Here in Module 6, we'll more focus on experiments. If a statistical researcher wants to prove a cause and effect relationship between two variables, they're going to have to use an experiment, as we talked about in previous modules, because an observational statistical report it shows an association, like we said, but it doesn't show cause and effect. So an experiment intentionally manipulates the explanatory variable, as we've kind of talked about before, in an attempt to cause an effect on the response variable. So that's a little bit of review, just in case you forgot what experiment is. Hopefully you wrote it down in your notes. But in order to establish a cause and effect relationship, they need to show that there are no confounding variables. We talked about confounding variables, excuse me, a little bit before. They're variables that could affect the outcome, that might make it so we can't say that the particular variable that we're interested in doesn't actually cause an effect on the second variable we're interested in. Maybe it's an outside variable we haven't considered yet. So what they need to do as researchers, they need to somehow make sure that these confounding variables aren't a factor. So here it kind of talks about the word confound in general. To confound means to mix up or confuse. So confounding variables mix up our ability to determine if the explanatory variable causes a change in the response variable. If you don't control the effects of the confounding variables, then you can't really prove a cause and effect relationship between the explanatory variable and the response variable that you're interested in. So there are two strategies researchers use to control the effects of confounding variables. And we'll talk more about them. We haven't really talked about these yet. This is kind of a new concept. The first one's called direct control, which the terminology is kind of nice. I like the way they chose the words, because it kind of gives you a hint as to what it means, and random assignment. So let's first talk about direct control. In this first example, they have an experiment with researchers comparing bacteria reduction for 3 different hand drying methods. So, if you use a public restroom, sometimes there are towels, you can use paper towels, and then sometimes there's the air dryers. So just seeing the effects, how much bacteria is still on your hands if you do one versus another. So in this experiment, participants handled uncooked chicken for 45 seconds. So of course, there's a lot of bacteria, obviously, on uncooked chicken. Then they washed their hands with 1 squirt of soap. So they're kind of using a lot of control here. They're making sure that everybody touches the chicken for the same amount of time, it's 45 seconds, and they use exactly the same amount of soap, and they wash their hands for the same amount of time. So those could all be confounding variables. One person might have handled the chicken for longer, so they have more bacteria, or one person might have used more soap, another might have washed their hands for longer. So they've kind of tried to control all those variables and made sure that everybody has the same baseline. And then used one of 3 hand drying methods. After participants completely dried their hands, researchers measured the bacteria on their hands. The results were published in 2010. In this experiment, the explanatory variable is the hand drying method. So that's the one that we're thinking will explain why there would be a certain amount of bacteria left on someone's hands. Maybe the paper is better, or the air drying method is better. But in this case, the response variable is the bacteria count. So what is causing it? What is explaining the bacteria count is the hand drying method, but the variable that's responding to the hand drying method is the bacteria count. Notice that the explanatory variable determines the 3 treatments in the experiment. So each treatment is a different hand drying method. For this reason, the explanatory variable is also called the treatment variable. In this experiment, researchers attempted to directly control the influence of 3 variables that could affect the bacteria count. So here it kind of lays out what we were talking about. These are the ways that the researchers had direct control over this experiment. First, they controlled the length of time participants took to dry their hands, to handle the raw chicken. So they had direct control over that because everybody handled the chicken for 45 seconds. The other one is the amount of soap that participants used. All participants used only 1 squirt of soap. The amount of time participants washed their hands, all participants were made to wash their hands for exactly 60 seconds, no longer, no less. So it says here, now, notice that control works by stabilizing the impact of the confounding variables across the treatments, as we kind of mentioned a little earlier. So as I kind of explained further here, if all participants use the same amount of soap, for example, or hold the chicken for the same amount of time, wash their hands for the same amount of time, then the bacteria count of the 3 treatments cannot be due to the amount of soap used, or the amount of time that they held the chicken, or the amount of time that they took to wash their hands. So it should be, if they've come up with all the confounding variables at least, then that means that the method of drying hands should be the explanatory variable. And then they say here, similarly, the amount of time it takes that participants will wash their hands, as we kind of mentioned, that should kind of get rid of any confounding variables. Now let's examine the random assignment. So that's the other thing that we mentioned, that we want to make sure that everything's random because it controls the effects of confounding variables that the researcher cannot control directly, or that difficult to identify in advance. Like, I guess the difference between people and... So that's the end of that example. I can kind of wish we would know which hand drying method was the best, but anyway, we'll probably come back to that in a future example. So another different example of random assignment is, in this one, medical researchers conducted an experiment to compare 2 different types of surgery for children with hernias. They compared the recovery times for each type of surgery. So that way, then they know which one's better, and they'd only offer the one if it's much better in the future. So there are 2 surgery types. One's laparoscopic. I guess it involves 3 small incisions, and the other one's open repair, where it involves 1 large incision. So they identified a variety of variables that might influence recovery time, such as the child's age, weight, and physical fitness. So if they only studied 2 children, I guess, like one that had 1 type of surgery, the other that had the second type of surgery, they couldn't really say one surgery is better than the other, because it could be due to the differences between the children. As they've mentioned here, the child's age, weight, and physical fitness level, for example, or maybe even a few other confounding variables. So here they ask, how could the researchers control the impact of age on recovery time? Well, one thing they could do is just make sure that they only study children that are the exact same age. So that's what they did. They only looked at children that are 10 years old in this experiment, and they had to have hernia surgery. But it might be difficult to find enough 10-year-olds with hernias, so that's a problem. One way they can fix this is to assign children at random to treatment groups. Just even though they can't only look at children that are 10 years old because there's not enough of them to study that have to have hernia surgery, maybe if they randomly assign children of all ages into these 2 groups that are having the different surgeries, there's just enough variety to where the age doesn't matter. So now they're going to illustrate how this random assignment they mentioned actually creates similar groups to where the confounding variables wouldn't be a factor anymore. So below is a dot plot of the ages of 48 children with hernias who participated in this experiment. Each of the dots in this figure here represents a child who had to have the surgery. So the average age of these children is 8.29 years. Okay, if random assignment is working, the average age for each treatment group should be about equal. Yeah. And of course, you can kind of imagine if the more children that are involved in this experiment, probably the more random the assignment actually is. But if you use very few, we've kind of seen that before, where the number in your sample, the higher it is, the more random and the better results you're going to get. But the fewer people in your sample, or the fewer items or animals, probably the less random the assignment will be. So down here we have one of these applets that we can try. We're going to click the random assignment button to randomly generate 48 children to the 2 treatments. Repeat this process several times to investigate whether random assignment creates groups with similar ages. So we'll see the average age labeled as the mean and marked with a vertical line. Compare the average ages for the treatment groups. Okay. Let's see what we get here. I'm going to press it once. It looks like already the means are 8.29, 8.32, and 8.26. Let me press it again. The total, the total here, let's see, here, 8.29, that's going to stay the same because that's total. But here we're looking at a random assignment of 48 children. It looked like first the mean, I got 8.76, which is a little higher than the mean we circled above. Treatment 2, though, they randomly assigned, it looks like the age is a little, lower by 1 year or so than the red mean that you see there. Okay, let's try to press it again and see what happens. Randomly generate new groups. It looks like the first mean changed. Now it's much higher, 9.64, which is more than a year. The average child in that group is more than a year older than the mean of the total group. And here the mean is way younger. So sometimes random assignment doesn't work super well because just, it's chance. You happen to get a group of mostly young people or mostly older children. So probably if you want to do random assignment, you might want to try it multiple times to get an average like we're doing, or have a group or a sample size of a higher number. But maybe in this case, not a lot of children are getting this surgery, so it's hard to get a larger group. Maybe we'll try it. Let's try it one more time. All right, this looks a little closer to the above mean, the total mean, the one that's in black writing. The red mean, the one that's in red writing, is 7.68, which is lower, a lower age than the mean of the total, but it's not too far off. And then the blue, the blue mean for treatment 2, the age is a little higher than average, 8.96, but it's not too far off. So this one might have been a good sample, but it's just chance that gets us to have a good sample or not. So overall, what are we trying to say with these examples? The goal of random assignment is to create similar treatment groups. If the groups are similar, then any differences we see in the response variable are due to the differences in treatments, not due to the differences in the groups. In this way, random assignment controls the impact of confounding variables. Random assignment is eliminates confounding, just as random selection in a survey eliminates bias. So how do we make random assignments? We use any method that allows random chance to choose the treatment for each patient. Either, like they say, we'll pick names out of a hat, which I guess is not really practical, but a lot of times, as we mentioned in previous videos, a computer program chooses it for us. That way, there's no bias. A computer doesn't have bias unless you program it into it. But that way, each participant has an equal chance of receiving either of the treatments, as in this example above. So in the hernia experiment above, you could put every child's name in a hat, like we mentioned, or you could put every child's name in a computer program and it would choose randomly for you.
Love you.